This example comes out of section 3.1. We're talking about the beginning of applications of derivatives, and 3.1 is about velocity. We start off and we'll be given some kind of function of time where position is a function of time. They like to use the letter s for our position or distance in meters, just because d's become I guess we see so many d's when we're doing derivatives. If you find the rate of change, delta s over delta t, what you're finding is velocity. And so we could find average velocities by figuring out a total distance divided by total time, but instantaneous velocity is what we're more interested in here, is going to be the derivative ds by dt, or if you prefer s prime or f prime of t. Any one of those things is equal to our velocity function. And so we'll do an example of a question here, and it kind of looks just like a physics 20 question, and then you realize that with this simple calculus equation we can solve the same things we did in physics. So our question sets up like this. We're dropping a book from a tall building, 325 meter building, and we're told that its height in meters is given by h equals 325 minus 4.9 t squared, where t is in seconds. We're asked to find the velocity after 2 seconds, after 3 seconds, asked when will the book hit the ground, and then with what velocity. Those of you that have taken physics will recognize when we take the derivative of this, like dh by dt, our change in height over change in time, that's our velocity. And so it's going to be 0 minus 9.8 times t. That 9.8 basically is there because of gravity. 9.81 is probably what you learned if you took physics. And that's fine, that's true. We're assuming no air resistance and all those kinds of things. So if we wanted after 2 seconds, we'd say, well, v of 2 is negative 9.8 times 2, which is negative 19.6 meters per second. So it's cruising pretty fast. After 3 seconds, even faster, down towards the ground, times 3 gives me negative 29.4 meters per second. And so this thing is getting faster and faster towards the ground until it finally hits the ground, in which case obviously it just will slam. When will it hit the ground is taking the original function we were given and saying, well, let's let h equals 0. So 0 equals 325 minus 4.9 t squared. We're not actually doing any calculus in that part of the situation here. We're just saying, well, t squared is going to equal 325 divided by 4.9. So t is going to be the square root of that. And we don't need the negative answer, so the positive answer is what we get. And I crunch the numbers and I get approximately 8.1 seconds. It takes, again, assuming no air resistance or anything else, with gravity and a height of 325 meters, it takes a while to hit the ground. 8.1 seconds. With what velocity? We just take that and say, well, the velocity after 8.1 seconds is going to be negative 9.8 times 8.1, which gives you approximately 79.8 meters per second. Negative, just meaning that it's falling towards the ground at that rate. So again, a question that, with d equals vit plus 1/2 at squared, and acceleration equals vf minus vi over t, and all these equations that you had on the physics 20 formula sheet, you could do these questions, but now maybe you're starting to see where some of those equations on the formula sheet actually came from.